Hi, my name is Abigail, and this is my Physics Lab 2 on the motion of a falling object. For the introduction, in this lab we will observe a falling object from rest from 1 meter. In my case, I crumpled up a piece of notebook paper and dropped it for a meter. From this, I used the tracker software to track the object's fall path and also use it coded using computational models on GlowScript, which will compare the difference between just using gravity and using both gravity and drag to track the fall path. And the system in question for this lab is the crumpled piece of paper, and the surroundings are everything else. Just some key physics concepts that I want to go over before we dive into the data and code. The force of gravity is measured by negative direction and the mass times the acceleration of gravity due to Earth's surface, which I included was 9.8 meters per second squared. And then the force of drag is equal to negative b, which is the constant, times v squared and v hat. And v hat is the directional vector, and then v squared is going to be the magnitude of the velocity vector. I also included the velocity update formula and the position update formula because they are used in the code, and it is helpful to find out, like, hey, how's the velocity changing and what's happening to the position due to the initial position, and adding that average velocity, which really helps during the computational models. And this is exactly what I put into my code to calculate the final velocity and calculate the final position. So it would do everything for me and ensure no errors in that part. So yeah, that's the key physics concepts for this lab. Looking at the data, you can see the blue is the tracker data, the red is the computational with gravity only, and the yellow is the computational with drag plus gravity. You can see that the drag is very much a lot closer to the tracker data. It's still a little bit off, which could be because we were doing some guess and check with the coefficient, the b variable. We weren't really fully calculating that, so it may still be a little bit off, and that's why it's not fully aligned. But with the gravity, you can see it doesn't account for drag, so it's going to fall much faster. And I do want to add that it's like going towards the origin from a negative perspective, instead of falling from a positive space to the origin. It's like falling from a negative space, so that's why my graph is flipped in that perspective. But you can see the y position on the y component, and then the time in seconds on the bottom, which it only took about 0.4 seconds. So for the discussion, what does it mean, and the what if parts, what does it mean? Well, the question for that was which models predict a terminal velocity, and then looking at the velocity versus time graphs, how can we tell? So the computational model that uses the drag force, we can see that is the model that most predicts a terminal velocity. And this is because in the velocity versus time graph, we observe that change in slope towards the end of the time interval. And the slope decreases, which suggests an asymptote. It starts to kind of hug a certain velocity. And so that asymptote is actually going to be the terminal velocity. And what if we threw the object instead of dropping it from rest? So that would change the initial velocity. And by throwing the object downward, it's going to fall at a greater rate. But the computational model will show that the terminal velocity stays the same. And you can see that by just changing in your GlowScript code the initial conditions. And that's basically going to change everything for you. And then it's just going to show that it's going to reach your terminal velocity at an earlier time, but it's still going to be the same terminal velocity as the first part of the discussion question. Thank you for listening to my lab. I appreciate it, and have a great day.